Hello and welcome back to Chapter 6, Problem Bank. This is number 19. We're dealing with elastic collisions, which means that all energy is conserved. A highly elastic rubber ball is tossed at a movable wooden wall panel that is initially at rest. The ball's initial velocity is 6 meters per second to the right. After the elastic collision, the ball returns with a velocity of 4.9 meters per second to the left, while the panel moves 1.09 meters per second to the right. If the panel's mass is 1.25 kilograms, what is the mass of the ball? First thing that we will write down is that positive will be to the right, and we decided that. Our given is that we have the velocity of the panel initially is 0. We are given that the ball's initial velocity is 6.0 meters per second. We are given that the final velocity of the panel is equal to 1.09 meters per second. And we are given the panel's mass. Our unknown is the mass of the ball. The equation we'll use, the most simple one would be our initial momentum, which would be the mass of the ball times the velocity initially of the ball plus the mass of the panel times the initial velocity of the panel is equal to mass of the ball times the final velocity of the ball plus the mass of the panel times the final velocity of the panel. Substitute in what we're given. We'll see that because the velocity of our panel is 0, our momentum will be 0. And we're looking for the mass of the ball. Our initial velocity of the ball was 6. This is equal to the mass of the ball times the final velocity, which is a negative 4.9 meters per second. As you see, I forgot that out of the given portion. That's okay, we got it now. Mass of the panel, 1.25 times 1.09. As we solve this for m sub b, we see that we'll end up with 10.9 times m sub b, and we get that from adding 4.9 m sub b to both sides. That is equal to 1.25 times 1.09. which is equal to 1.36. We're going to divide that by 10.9. And we're going to see that the mass of the ball is equal to 0.125 kilograms. Number 21, again, still dealing with elastic collision. A 20 kilogram object sitting at rest is struck elastically in a head-on collision with a 10 kilogram object initially moving at 3 meters per second. Find the final velocity of the 20 kilogram object after the collision. So again, we will say that positive is to the right. We are given mass of the first object is equal to 20 kilograms. The velocity initially of the first object is equal to 0 because it is at rest. The mass of the second object is equal to 10 kilograms. And the initial velocity of the second object is equal to 3 meters per second. And we are going to look for V sub F of the first object, or the 20 kilogram object. Doesn't really matter how you use your subscripts as long as you can keep them identified and you know what you're solving for and you plug everything in correctly. So our equations are going to be, one is going to be our conservation momentum, which is going to say the momentum initially of the first object plus momentum initially of the second object is equal to the final momentum of the first object plus the final momentum of the second object. We will also use that because we have a elastic collision and because we have not enough knowns to find our unknown, we'll use our velocity initial of the first object plus the velocity final of the first object is equal to the velocity initially of the second object plus the velocity final of the second object. So substituting everything in, we see that our momentum of initially of our first object is 0 because mass times velocity, which is 0, is going to equal 0 plus 10 times some velocity. And we do know that velocity, and that velocity is 3. This is equal to the final momentum of the first object, which is going to be 20 times V sub F sub 1 plus the momentum of the second object, which is 10 times V sub F sub 2. Again, we are looking for the velocity of the 20 kilogram object after the collision. Notice how our masses did not change after the collision, which makes sense because they bounced off of each other. And let's plug in what we know here. We know Our initial velocity of the first object was 0, and we do not know the final velocity, so we'll put that as such. We do know the initial velocity of the second object, which was 3, and we do not know the final velocity of the second object. Now, because we are looking for v sub f sub 1, we need to solve preferably, I would say, this second equation for v sub f sub 2. So when we end up substituting in, we'll be left with the one lone variable is v sub f sub 1, which will save us some work at the end. So here I'm going to minus 3 from both sides. That takes care of that, and we have v sub f sub 2. So what we're going to do is we're going to take what is equal to v sub f sub 2 and substitute it in. So rewriting and solving our equation, we see that 3 times 10 is 30. And that is equal to 20 times v sub f sub 1 plus 10 times this quantity. So I'll write that out. Then we'll distribute our 10. Simplifying that, we're going to end up with 60 is equal to 30 v sub f sub 1 divided by 30 on both sides. That crosses that out. And we end up with the final velocity of the first object, which we called our 20 kilogram object, is equal to 2 meters per second. Now, if you remember doing this problem in class, you will see that we had a lot harder time doing that because we did not have that, or we did not use that equation. We used the conservation of energy, which is our 1/2 mv squared equation, final and initial. But using this, we did not have to deal with the squared velocities, and that was everything was to the first degree and made things a lot simpler. Number 23. A 2,500 kilogram truck moving at 10 meters per second strikes a car waiting at a traffic light. Hooking bumpers, the two continue to move together at 7 meters per second. What was the mass of the struck car? So here we've gone from elastic collisions to perfectly inelastic collision. The reason this is perfectly inelastic collision is because we are looking at two things that hooked bumpers. That means that they are stuck together. So we are given that the mass of the truck is equal to 2,500 kilograms. The velocity initially of the truck is equal to 10 meters per second. The initial velocity of the car is equal to 0 because we were waiting at a traffic light. And we know that the final combined velocity and we'll just put combined is equal to 7 meters per second. I'll give this another subscript so we don't get the two C's confused. So our unknown again is the mass of the car. Our equation is going to be the momentum initially of the truck plus the momentum initially of the car is equal to the momentum of everything that's combined. And again, that looks like m sub t, I'll rewrite that, times v sub t initially plus m sub c times v sub c initially is equal to our two masses times the total velocity, or the combined velocity, I should say. So substituting everything in, we know that because our car was at rest, we'll have zero momentum for that. And we have 2,500 times our initial velocity, which is 10, is equal to 2,500 plus the mass of the car times 7. Now I didn't do a frame of reference here, and probably doesn't hurt to do so. Positive going the one way. But because we have an inelastic collision, we know that we do not have any energy going in two directions. We just have energy from the truck moving in the one direction. Therefore, we know that our final combined mass is can only go the one direction. So solving this, we get 25,000 here is equal to 7 times 2,500. 17,500 plus 7 times the mass of the car. Solving that out, we get 7,500 here is equal to 7 mass of the car divided by 7. This is going to be equal to 1,071. So just call that 1,100 kilograms. 1,100 kilograms. Again, that is the mass of the car. Which makes sense because trucks usually do weigh more than cars. All right, number 25. During a snowball fight, two balls with masses of 0.4 and 0.6 kilograms are thrown in such a manner that they meet head-on and combine to form a single mass. The magnitude of the initial velocity for each is 15 meters per second. What is the speed of the 1 kilogram mass immediately after the collision? So it told you the final mass right here, 1 kilogram, and that makes sense because 0.4 times 0.6 is equal to 1. And we know that we have a perfectly inelastic collision because we are, again, combining to form a single mass. So we are given the mass of the first snowball, 0.4, the mass of the second snowball, 0.6, the initial velocity of each, which is 15 meters per second. And let's make sure, let's break that up. So we'll call the first snowball our 0.4, and we'll say that is going to the right. positive is going to the right. So the point 4, the initial velocity of the first snowball is equal to 15 meters per second. And the initial velocity of the second one is equal to a negative 15 meters per second. Again, they were thrown in such a manner that they meet head on. So our unknown is the speed of the combined mass. We'll just call that V sub F. Our equation be the momentum of the first snowball plus the momentum, of the second snowball is equal to the combined mass times the final velocity. So we'll substitute things in, and we have 0.4 times 15 plus 0.6 times a negative 15 is equal to 1 times V sub F. Solving that, we get 0.4 times 15 is equal to 6 plus 0.6 times 15 that's going to be a negative 9 equals V sub F, and so we see that negative 3 is equal to V sub F. So that means that if we were looking at a diagram, our snowball would be going to the left. But I can hear arguments that if we decide to go with what we learned in the first chapter, maybe the second, that speed is just the magnitude and velocity is the direction. It did not ask for the velocity. So I guess we could say that the speed of the snowball is just equal to the speed of the snowball. Speed of the snowball is equal to 3 meters per second. Number 27, a railway car with mass of 8,500 kilograms and velocity of 4.5 meters per second. To the right collides inelastically with a railway car with mass of 9,800 kilograms and velocity of 3.9 meters per second to the left. What is the final velocity of the combined cars? So we will create our frame of reference by saying that positive will be to the right. And we are given that the mass of railway car number 1 is 8,500 kilograms. The mass of railway car number 2 is equal to 9,800 kilograms. The velocity of initially of car number 1 is to the right, so that will be positive at 4.5 meters per second. Velocity of car number 2 initially, which is going to the left, is a negative 3.9 meters per second. with our unknown being the final velocity v sub f. Our equation be the same one that we've used because we again are looking for a combined velocity. Momentum of the first object plus momentum of the second object is equal to the combined masses times their final velocity. Substituting everything in, we have 8,500 times 4.5 plus 9,800 times a negative 3.9 is equal to 8,500 plus 9,800, which will be 18,300 times our final velocity. Solving the equation for v sub f, we get 8,500 times 4.5 minus 9,800 times a negative 3.9 and let me calculate that one more time. And we get 30, and this is a positive 30, so we know that our momentum is still going to the right. We're going to divide that by 18,300 v sub f, and our final velocity is very, very small, 0.002 meters per second. All right, last one. A swimmer with a mass of 58 kilograms and a velocity of 1.6 meters per second to the north climbs onto a 142 kilogram raft. The combined velocity of the swimmer and the raft is 0.32 meters per second to the north. What is the raft's velocity before the swimmer reaches it? So we'll say that positive is to the north. We are given that the mass of the swimmer is equal to 58 kilograms. The initial velocity of the swimmer is equal to 1.6 meters per second. The mass of the raft is equal to 142. And the final velocity is equal to 0.32 meters per second. And our unknown is the initial velocity of the raft. Our equation is going to be the initial momentum of the swimmer plus the momentum of the raft is equal to the combined masses multiplied by their final velocity. Substitute in our knowns, and we know that our momentum is mass times velocity. And again, we do not know our initial velocity of our raft, so we do not know our initial momentum. The swimmer and the raft, that mass combined will be 200 kilograms, and the final velocity is 0.32. Solving that, we get 58 times 1.6, 92.8 plus 142 VIR is equal to 200 times 0.32, 64. Solving for V sub IR, we're going to subtract 92.8 from both sides, and we're going to divide by 142. So 64 minus 92.8 equals a negative 28.8. We're going to divide that by 142. And we have the initial velocity of the raft at a negative 0.20 meters per second, which also means that our raft initially is heading south. That's it for Chapter 6, problems involving elastic and perfectly inelastic collisions.